Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. There's something quietly haunting about standing beneath a clear night sky, far from the city lights, where the stars appear, not as distant pinpricks, but as an ocean of ancient whispers. You tilt your head back, and there they are, thousands upon thousands of them, scattered across the darkness, like diamonds spilled across black velvet. And in that moment, you might feel small, you might feel alone. But here's what you probably don't realize. You're not looking at the present. You're looking at history. Every photon of light that reaches your eye tonight began its journey long before this moment. Some started traveling when you were a child. Others when your grandparents were young. And some began their voyage when civilizations we now study in history books were just being born. The night sky isn't a snapshot of now. It's a museum, a gallery of the past, stretched across the cosmos, waiting for us to understand what we are really seeing. Take Betelgeuse, for example. You might know it better by its more playful name, Betelgeuse. It's one of the brightest stars in our sky, the red giant that marks the shoulder of Orion the Hunter. Right now, as you imagine looking up at it, you are seeing light that left that star approximately 640 years ago. Pause and think about that. When the light you see tonight first departed from Betelgeuse, Johannes Gutenberg had just invented the printing press. The Renaissance was dawning. The Americas were, to Europeans, undiscovered. And Shakespeare wouldn't be born for more than a century. And here's the truly unsettling part. Betelgeuse might not even exist anymore. Not in the way we think of it, anyway. This massive, unstable star could have already exploded in a spectacular supernova, an event so bright it would briefly outshine the full moon in our sky, visible even during the day. But because it is so far away, the light from that explosion wouldn't reach us for hundreds of years. We could be walking beneath a sky that shows us a star that has already died, completely unaware that the universe has already moved on. This is the strange and beautiful truth about cosmic distances. When we measure them in light years, the distance light travels in 1 year. We are not just talking about space. We are talking about time. We are talking about looking backward through history. With every glance upward, we are talking about a universe where now does not exist the way we think it does, where simultaneity breaks down, where the very act of seeing becomes an act of remembering. Light years don't just measure how far away something is. They measure when we are seeing it from. They turn our telescopes into time machines, and our eyes into windows to the past. They remind us that in the vastness of space, distance and time become two sides of the same cosmic coin. Tonight, we're going on a journey, a slow journey, a deep journey, a journey through space and through time. We are going to explore what light years really mean, not just as a number in a textbook, not just as a scientific definition, but as a concept that quietly and profoundly changes how we understand reality. We will drift from our moon, step by step, across the darkness, to the very edge of the observable universe. We will visit distant, alien worlds, worlds that might, just might, harbor life. We will sit with the loneliness of cosmic distances and feel how vast, how empty, and how silent space truly is. We will gently unpack the strange, bending, mind-twisting implications of Einstein's relativity, and we will ask a difficult question, a question that echoes through the galaxy. In a Milky Way filled with 400 billion stars, why do we feel so utterly and eerily alone? Pause, and maybe, just maybe, by the end of this journey, we will begin to understand why light years break our brains, and why that is actually something beautiful. Because in realizing how small we are, how isolated we are, how brief our existence is, against billions of years of cosmic time, we also discover something deeply meaningful. We are not separate from the universe. We are the universe, looking back at itself. We are stardust that learned to think, to feel, to wonder, and that, perhaps, makes us one of the most extraordinary things in all those endless light years of space. So now, dim the lights, let your breathing slow, Let your thoughts soften. Allow your mind to expand beyond your body, beyond Earth, beyond even the stars, and prepare to see the cosmos, not as it is right now, but as it was, as it always has been, and always will be, in the eternal now. That is the past. Before we can truly understand the distances that separate us from the stars, we need to understand light itself. And to understand light, we need to appreciate just how fast it moves. Pause. Light is, quite simply, the fastest thing in the universe. Nothing can move faster. According to Einstein's theory of relativity, it is not just a speed limit. It is the speed limit, woven into the very fabric of reality itself. Light travels at approximately 300,000 kilometers per second. Let that sink in slowly. Every single second, a beam of light covers 300,000 kilometers. That is roughly the distance from Earth to the Moon, and it covers that distance in just over 1 second. Pause, breathe. To put this in human terms, imagine you are sitting in a car on an empty highway. You are going 100 kilometers per hour, which feels quite fast. At that speed, it would take you about 446 days of continuous driving, more than a year, to cover the distance. Light travels in a single second. A commercial jet, flying at 900 kilometers per hour, would need almost 2 weeks to match what light does. In the blink of an eye. Pause. Or think about it this way. If you could walk at a steady 5 kilometers per hour, never stopping, never sleeping, never resting, it would take you nearly 7 years to walk the distance. Light travels in 1 second. 7 years of walking for 1 second of light's journey. The scale is almost incomprehensible. And we are still talking about a single second. Pause. Now, let us extend this. A light year is the distance light travels, not in 1 second, but in 1 full year. An entire orbit of Earth around the Sun. 365 days, each with 24 hours, each hour with 3,600 seconds, and in every single one of those seconds, light is racing forward at 300,000 kilometers per second. When you multiply it all out, 1 light year equals approximately 9.46 trillion kilometers. That is 9,460 billion kilometers. The number is so large, it becomes almost meaningless. Our brains did not evolve to grasp distances like this. We evolved to estimate the distance to the next tree, the next water source, the neighboring village. Trillions of kilometers might as well be infinity. Pause. But here is where it gets interesting. A light year is not really about distance in the way we normally think about it. It is about distance wrapped in time. It is a measurement that binds space and time together, making them inseparable. When we say something is 4 light years away, we are not just saying it is far. We are saying that the light we see from it right now left 4 years ago. We are saying that we are looking for years into the past. Pause. Think of it like this. Imagine you are watching a movie, but the movie is the universe, and every star is an actor on an unimaginably vast stage. The catch is, each actor is performing their scene at a different time, and you are seeing all those different times simultaneously, mixed together in your view of the night sky. The star closest to you might be showing you what happened 4 years ago. The next star over 8 years ago. Another 600 years ago. And the most distant galaxies we can see, they are showing us what happened over 13 billion years ago, when the universe was young, and our corner of space did not even exist yet. Pause. This is the magic and the madness of light years. They force us to think about space and time, not as separate things, but as a unified whole. What physicists call space-time. They remind us that now is a local phenomenon, something that only makes sense in your immediate vicinity. The further out you look, the further back in time you see. There is no universal present moment, no cosmic now, where everything exists simultaneously. There is only the here and now of your location, and the there and then of everything else. Pause. When ancient humans looked up at the stars, they thought they were seeing holes in a celestial sphere, or perhaps the distant fires of gods. In a way, they were closer to the truth than they realized. They were seeing ancient light, stories written in photons, messages from the past that had been traveling through the void for longer than human civilization has existed. A light year is not just a unit of measurement. It is a reminder that the universe is written in time, as much as in space. That distance and history are the same thing on cosmic scales, and that every time we look up, we are archaeologists excavating the past with our eyes. Pause. And now that we understand what a light year is, we can begin to truly explore what it means. We can start to comprehend the distances that separate us from everything else in the cosmos. We can begin to feel the weight of the void and the strange beauty of living in a universe where everything we see has already happened, where the present is always somewhere else, and where the stars are memories painted across the sky. If you've ever looked up at the moon on a clear night, you have already experienced the concept we are exploring, even if you didn't realize it. The moon, our closest celestial neighbor, orbits Earth at an average distance of about 384,000 kilometers. That sounds enormous, and by human standards, it is. But light, traveling at its incredible speed, covers that distance in just 1.3 seconds. Pause. This means that when you look at the moon, you are not seeing it as it exists in this exact moment. You are seeing it as it was 1.3 seconds ago. The light hitting your eyes right now left the moon's surface just before you could even say the word light. It is a tiny delay, barely noticeable, almost trivial, but it is real. You are looking into the very recent past. Pause. Now, let us move a little farther out. Every morning, the sun rises and bathes our world in light and warmth. We take it for granted. This steady, reliable star that makes life possible. But that sunlight, it is already old. By the time it reaches you, the sun sits about 150 million kilometers away, and light takes about 8 minutes and 20 seconds to cross that distance. Pause, breathe. Think about what this means. If the sun suddenly vanished, right now, in this very instant, we would not know. For more than 8 minutes, we would still see it shining, still feel its warmth, completely unaware that our star was already gone. For 8 minutes and 20 seconds, we would be living in a universe that had already changed. But the information about that change would not have reached us yet. We would be living in the past. Pause. This is true. For every interaction we have with the sun, those beautiful images from solar observatories, they show us the sun as it looked 8 minutes ago. Those powerful solar flares that can disrupt satellites and power grids. By the time we see them erupting, they have already been happening for 8 minutes. We are always behind, always catching up to a reality that has already moved on. Pause. Now, let us journey farther. Sirius, the brightest star in our night sky. After our own sun, it sits 8.6 light years away. When you see Sirius twinkling on a cold winter night, you are seeing light that began its journey 8.6 years ago. If you are 25 years old, that light left Sirius when you were 16, maybe in high school, dealing with homework, friendships, and worries that felt so important then. In a strange way, the light you are seeing now is a messenger from your own past. It was already traveling while you were living that chapter of your life. Pause. Polaris, the North Star, our ancient navigational guide. It lies about 433 light years away. The light you see tonight left that star in the late 16th century. When that light began its journey, Shakespeare was writing his plays. The Mughal Empire was flourishing in India. The Ming Dynasty ruled China. That single photon of light has traveled through empty space, through centuries of human history, through exploration, revolutions, wars, the rise of nations, the birth of the modern world, all to finally arrive at your eye tonight. Pause. And here is something truly mind-bending. The Polaris you see is not exactly the Polaris that medieval navigators used. It is the same star. Yes, but not in the same place. Stars move. They orbit the galaxy, just like our sun does. Over centuries, their positions shift. So the Polaris of 1600 was in a slightly different location than the Polaris of today. But we are seeing where it was 433 years ago, not where it is now. If we could somehow see its true current position, it would be in a different spot entirely. But we will not see that for another 433 years. Pause. This creates a strange layering of time. In the night sky, every star you see belongs to a different era. Some are showing you the 1980s. Some are showing you the Renaissance. Some are showing you ancient Rome, ancient Egypt, even the Stone Age. The farthest stars visible to your naked eye are showing you a world that existed thousands of years before writing itself. Pause. In essence, your eyes are a time machine, not in a science fiction sense, but in a very real way. You are seeing the past. You are receiving information about states of reality that no longer exist. The universe you observe is a patchwork of different moments in history, all stitched together by the speed of light and the vastness of space. Pause. The sky is a museum, yes, but it is also a cosmic archive, a vast library of light, where every book comes from a different time, and you are reading them all at once. The moon is the newest edition, published just over a second ago. The sun is the morning newspaper from 8 minutes past. Sirius is like a yearbook from your teenage years. Polaris is a Renaissance manuscript, and the distant galaxies, they are ancient scrolls from the dawn of time itself. Pause. This is not just astronomy trivia. It is a fundamental feature of reality. The speed of light is finite, and space is vast. So the past is all we ever see. When we look outward, the present exists only here, only now, only in this exact place. Everything else is memory, frozen in photons, traveling across the void. Pause. And maybe there is something beautiful in that. Maybe it is fitting that when we look into the cosmos, we are also looking back through our own history, through the history of our world, through the history of life, civilization, and everything that has ever happened. Perhaps the universe is reminding us that the past is not truly gone. It is just very, very far away, encoded in light, waiting to be seen. Now let's take a proper tour of our cosmic backyard. The stars that are closest to us, the ones that define our little corner of the Milky Way galaxy. These are our neighbors. Relatively speaking, though neighbor is a word that takes on a very different meaning when we're talking about light years. Pause. The nearest star to our sun is Proxima Centauri, part of a triple star system called Alpha Centauri. Proxima sits 4.24 light years away. That's about 40 trillion kilometers, or 25 trillion miles, if you prefer those units. Neither number really helps us comprehend the distance. So let's try this. If you could get in a car and drive toward Proxima Centauri at highway speeds, say 100 kilometers per hour, it would take you about 48 million years to get there. That's roughly the amount of time that's passed since the dinosaurs went extinct to now. Pause. But despite being our closest stellar neighbor, Proxima Centauri is invisible to the naked eye. It's a red dwarf, a small, cool star that emits only a fraction of the light our sun does. You need a telescope to see it at all. The light reaching us from Proxima left that star in late 2021 or early 2022, depending on when you're reading this. It's showing us the very recent past, but it's still the past. Pause. And here's something fascinating. Proxima Centauri has planets. We've discovered at least 2, possibly 3 worlds orbiting this dim red star. One of them, Proxima Centauri b, orbits within what we call the habitable zone, the region around a star where liquid water could theoretically exist on a planet's surface. Could there be life there? We don't know. But if there is, if there are beings looking back at us from that world, they're seeing Earth as it was 4.24 years ago. They're seeing our past, and we're seeing theirs. Pause. Moving outward, we encounter Barnard's star at 6 light years away. This star is special for a different reason. It has the largest proper motion of any star we know. Proper motion is the apparent movement of a star across the sky over time. And Barnard's star is racing through space relative to us. In about 10,000 years, it will actually be closer to us than Proxima Centauri is now. The sky changes, you see, just very, very slowly. Pause. Wolf 359 sits at 7.9 light years distant. A red dwarf so faint that even though it's relatively close, you need a fairly powerful telescope to spot it. The light we see from Wolf 359 began its journey in the mid-2010s, maybe around the time you were discovering YouTube, or learning about smartphones, or navigating some earlier version of the world we live in now. Pause. Then there's Sirius, which we mentioned earlier, 8.6 light years away. Sirius is actually a binary system, 2 stars orbiting each other. Sirius A is the bright star we see, a blue-white giant that's about twice as massive as our sun and 25 times more luminous. Its companion, Sirius B, is a white dwarf, the collapsed core of what was once a larger star. Sirius B is incredibly dense. A teaspoon of its material would weigh several tons on Earth. These 2 stars dance around each other, locked in a gravitational waltz. That takes about 50 years to complete. Pause. As we venture farther out, we find more stars, each with its own story. Epsilon Eridani, at 10.5 light-years, a sun-like star that might have its own planetary system. Tau Ceti, at 11.9 light-years, another sun-like star that's been the subject of many science fiction stories about potential life-bearing worlds. These stars are showing us what happened a decade or so ago. Light from them left around the time the first iPad was released, or when the world was recovering from the 2008 financial crisis. Pause. Within a sphere of 20 light-years around our Sun, there are roughly 100 stars. Most of them are red dwarfs, small and dim. Some are binary or multiple star systems. A few are sun-like, and virtually all of them are invisible to the naked eye, except for the brightest ones like Sirius and Procyon. Pause. What's striking is how empty space is, even in our neighborhood. If you shrunk the distance between the Sun and Proxima Centauri down to the width of the United States, from New York to Los Angeles, the Sun itself would be about the size of a basketball, and Proxima would be a baseball. On the opposite coast, and the space in between, nothing. Vacuum. Emptiness. A few atoms of hydrogen per cubic meter, perhaps, but essentially void. Pause. Yet even in this emptiness, things change. Stars are born, and stars die. They move through the galaxy at different speeds and in different directions. Our own Sun is traveling at about 230 kilometers per second as it orbits the Milky Way, and all the stars around us are doing the same, each on their own path. The constellation patterns we know and love, Orion, the Big Dipper, Cassiopeia, are temporary arrangements. Give it 100,000 years, and they'll be unrecognizable. The stars will have drifted apart, forming new patterns, new shapes in the sky. Pause. This is what our neighborhood looks like. A sparse scattering of stars, most of them faint, many of them accompanied by planets, all of them moving through space, on vast orbital paths around the center of our galaxy. When we look at these stars, we see them not as they are, but as they were. We see light years, not as distances, but as years of light travel. Each photon, a messenger from the past. Pause. And all of this, all 100 stars within 20 light years, represents just the tiniest fraction of our galaxy. It's like examining a single grain of sand and trying to imagine the entire beach. Our stellar neighborhood is vast by human standards, incomprehensible in its distances, and yet, it's barely a speck compared to what lies beyond. If we zoom out from our local neighborhood, out past the nearby stars, out past the hundreds and thousands of light years, we eventually see our galaxy as a whole. The Milky Way, our home, a vast spiral of stars and gas and dust and darkness, rotating slowly through the void, one galaxy among billions, and yet the only one we've ever known. Pause. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain because many stars are hidden behind dust clouds, and many more are too dim to detect. But even taking the lower estimate, 100 billion stars is a number that defeats comprehension. If you tried to count them one per second, it would take you more than 3,000 years to finish. Pause. Our sun is just one of these stars, and not a particularly special one. It's what astronomers call a G-type main sequence star, a yellow dwarf, medium-sized, middle-aged, ordinary in almost every way. It sits about 26,000 light years from the center of the galaxy, out in one of the spiral arms, in a relatively quiet region that has been stable enough for life to evolve and thrive on at least one of its planets. Pause. 26,000 light years to the galactic center. Think about that slowly. The light you would see if you could look directly at the core of the Milky Way, left there 26,000 years ago, when humans were still hunter-gatherers, when the last ice age was at its height, when there were no cities, no agriculture, no written language. That light has been traveling all this time just to reach this tiny spot in space where Earth happens to be right now. Pause. And the galaxy itself, the Milky Way, is about 100,000 light years in diameter. If you stood on one edge of the galactic disk and shone a flashlight toward the other edge, the light would take 100,000 years to arrive. Civilizations could rise and fall in the time it takes light to cross our galaxy. Pause. But the Milky Way is not just a flat disk. It is a spiral with several major arms curving out from the central bulge. We live in what is called the Orion Arm, or sometimes the Orion Spur, a minor arm located between two larger arms, Perseus and Sagittarius. From our vantage point inside the galaxy, We see the disk edge on, which is why the Milky Way appears as a glowing band of light across the night sky. When you are far from city lights, pause, and this entire structure, all 100 billion plus stars, all the planets, asteroids, and comets, all the gas clouds and dust, everything is rotating. The sun takes approximately 225 to 250 million years to complete one orbit around the galactic center. We call this a cosmic year or a galactic year. The last time the sun was in this exact position, dinosaurs were just beginning to dominate the Earth. The next time it comes around to this spot, who knows what will exist here? Perhaps nothing. Perhaps something we cannot even imagine. Pause. The rotation is not uniform. Stars closer to the center orbit faster. Stars farther out move more slowly. But here is something strange. The outer stars are moving faster than they should be, based on the visible mass of the galaxy. This is one of the great mysteries of astrophysics. Something invisible is adding mass to the galaxy, affecting the rotation rates. We call it dark matter, though that is really just a name, for we do not know what this is. It does not emit light, does not interact with normal matter, except through gravity, and it apparently makes up about 85% of all the matter in the universe. The galaxy you see, with all its stars, nebulae, and beauty, is just the tip of the iceberg. The bulk of it is invisible. At the center of the Milky Way lurks something even more mysterious and powerful, a supermassive black hole called Sagittarius A*, pronounced Sagittarius A star. It has a mass of about 4 million times that of our Sun, all compressed into a region smaller than our solar system. We can't see the black hole itself. By definition, nothing escapes from inside a black hole, not even light. But we can see the stars orbiting around it at incredible speeds, and we can detect the radiation from superheated materials spiraling into it. Pause. This black hole has been there for billions of years, sitting quietly at the heart of our galaxy, shaping the orbits of stars around it, growing slowly as it consumes gas, and occasionally an unlucky star. And like everything else, when we observe it, we are seeing it as it was, 26,000 years ago. If something dramatic happened there today, if a large star fell into it, creating a burst of radiation, we would not know. For 26,000 years. Pause. Scattered throughout the galaxy are nebulae, vast clouds of gas and dust, where new stars are being born. The Orion Nebula, visible to the naked eye, as a fuzzy patch in Orion's sword, is one of these stellar nurseries. It is about 1,300 light-years away, and it is actively forming stars right now. Or rather, it was actively forming stars 1,300 years ago, which is what we are seeing. Within these clouds, gravity pulls material together, compressing it until it gets hot enough to ignite nuclear fusion, and a new star is born. Pause. There are also the remnants of dead stars, planetary nebulae, where dying stars have shed their outer layers. Supernova remnants, the expanding shock waves from exploded stars, and neutron stars and black holes. The ultra-dense cores, left behind after massive stars die. The galaxy is a living ecosystem of birth and death, creation and destruction, all playing out over timescales that make human history look like a fleeting moment. Pause. If you could somehow step outside the Milky Way and view it from a distance, you would see a magnificent spiral, glowing with the light of billions of stars, with dark lanes of dust tracing the spiral arms, and a bright bulge at the center. You would see it slowly rotating, making one full turn every few 100 million years. You would see smaller satellite galaxies orbiting around it, like moths around a flame, some of them being gradually torn apart and absorbed by the Milky Way's gravity. Pause, and you would see that it is not alone. The Milky Way is part of a small group of galaxies called the Local Group, which includes Andromeda, another large spiral galaxy, and about 50 smaller dwarf galaxies. Andromeda is about 2.5 million light-years away, the most distant object visible to the naked eye. The light you see from Andromeda left that galaxy 2.5 million years ago, before modern humans existed, back when our ancestors were still learning to walk upright. Pause. Interestingly, Andromeda and the Milky Way are moving toward each other. In about 4 billion years, they will collide, or rather, merge, creating a new, larger galaxy that astronomers have nicknamed Milkomeda. But do not worry about this collision. Space is so empty. that stars almost never actually hit each other. The two galaxies will pass through each other, gravity pulling them back together, and they will eventually settle into a new shape, probably an elliptical galaxy. By then, the Sun will be nearing the end of its life anyway, so Earth's fate is sealed regardless. Pause. This is our galaxy, 100,000 light years of stars and stories, a spiral island universe that has been our home for as long as life has existed on Earth. When you look up at the Milky Way's band of light across the sky, you are seeing a cross-section of this structure. Billions of distant stars, all blending together into a river of light. You are seeing photons that have traveled for thousands or tens of thousands of years just to reach your eyes. You are seeing the past spread out across the sky, a reminder that in this vast cosmos, we are both insignificant and incredibly rare. For most of human history, we looked up at the stars and wondered, are there other worlds out there? It was a philosophical question, a matter of speculation and imagination. We had no way to know. The stars were too distant, planets too small and dim to detect. We could theorize, we could dream, but we couldn't confirm. Pause. That changed in 1992, when astronomers discovered the first confirmed exoplanets, planets orbiting stars other than our Sun. The floodgates opened as technology improved, as telescopes became more sensitive. We found more and more of these distant worlds. Today, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates waiting for verification. Pause. 5,000 worlds, 5,000 planets, orbiting distant stars, each one a potential laboratory for chemistry, geology, maybe even biology. Some are gas giants larger than Jupiter, orbiting so close to their stars that their surfaces are molten. Some are ice worlds in the outer darkness. Some are rocky planets like Earth, orbiting at distances where water could exist as a liquid. Pause. And the truly staggering thing, we've only searched a tiny fraction of the galaxy. We've looked at maybe a few 100,000 stars out of the 100 billion plus that exist in the Milky Way. Extrapolating from what we've found, astronomers estimate there are tens of billions of planets in our galaxy alone, tens of billions of worlds, each with its own story, its own history, its own potential for harboring life. Pause. Among all these discoveries, one system stands out as particularly intriguing. TRAPPIST-1. This small, cool red dwarf star sits about 40 light-years away from us, relatively close in cosmic terms. The light we see from TRAPPIST-1 today left that star in the early 1980s, when personal computers were just becoming common, when the internet was still a military project, when the world was a very different place. Pause. But TRAPPIST-1 is special, not because of the star itself, but because of what orbits it. 7 planets, 7 Earth-sized rocky worlds, all packed tightly around this dim red star. 3 of them orbit in the habitable zone, the region where temperatures might allow liquid water to exist on the surface. It's the largest number of Earth-sized planets we've found in a single system's habitable zone. Pause. The TRAPPIST-1 system is compact in a way that's hard to imagine. All 7 planets orbit closer to their star than Mercury orbits our Sun. If you stood on the surface of one of the TRAPPIST-1 planets, the other worlds would appear in your sky as large or larger than the Moon appears from Earth. You could see the neighboring planets in stunning detail with the naked eye. Clouds, continents, ice caps, all visible. If there were civilizations on these worlds, they would see each other's lights at night. They would watch weather systems move across each other's atmospheres. They would be tantalizingly close. Pause. But here's the paradox. Despite being so close to each other, the distance between these worlds might as well be infinite. Given our current technology, if humans on one TRAPPIST-1 planet wanted to visit another, they'd need spacecraft, propulsion, life support. It would still be a journey. And if they wanted to communicate with Earth, 40 years for a message to reach us, and 40 years for our reply to get back, an 80-year round trip for a simple hello. Think about trying to have a conversation with someone on the TRAPPIST-1 system. You send a message asking a question. If they receive it and respond immediately, you won't get their answer for 80 years. You'd be elderly or dead before you heard back. It would be less of a conversation and more like sending letters to the distant future, hoping someone receives them. hoping they care enough to respond. Pause. And yet, we can see these planets. We've detected them by watching the star's light dim slightly as the planets pass in front of it. A technique called the transit method. We've even analyzed the starlight passing through their atmospheres, looking for chemical signatures that might indicate water vapor, oxygen, methane, the building blocks of life as we know it. Pause. Could there be life on the TRAPPIST-1 planets? We don't know. The star is a red dwarf, which means it's cooler and dimmer than our sun, but also more prone to violent flares that could strip away planetary atmospheres. The planets are tidally locked, meaning one side always faces the star, while the other is in eternal darkness, which could make them less hospitable. Or it could create unique habitats, terminator zones, where the light and dark sides meet, regions of eternal twilight that might be perfect for life. Pause. We're still studying them, still gathering data, still trying to understand what these worlds are really like. But the very fact that they exist, that we've found them, that we can observe them from 40 light years away, is extraordinary. It's a reminder that the universe is far stranger and more wonderful than we imagined. It's a reminder that out there, in the darkness, are countless worlds we haven't discovered yet, some of which might harbor life, intelligence, civilizations, looking up at their own skies and wondering if they're alone. Pause. The discovery of exoplanets has fundamentally changed how we think about our place in the cosmos. We're not on the only world. We're not orbiting the only star with planets. We're part of a universe where planets are common, where every star you see might have its own system of worlds, where the potential for life is everywhere. Pause. But exoplanets also highlight the cruelty of cosmic distances. We can see these worlds, but we can't reach them. We can study their atmospheres, but we can't walk on their surfaces. We can send signals, but we can't have conversations. The light years that separate us from these planets are both a bridge and a barrier. They allow us to see, but they prevent us from touching. They let us dream, but they anchor us firmly in the reality of our isolation. Pause. TRAPPIST-1 is 40 light years away. That light left in the early 80s. When we look at those planets through our telescopes, we're seeing them as they were 40 years ago. We're seeing the past. If there's life there, if there are beings living on those worlds, we're watching their history unfold, not their present. And they, if they're looking back at us, are seeing Earth as it was 40 years ago, our past selves, living in a world that no longer exists. Pause. This is the haunting beauty of light years. This is what breaks our brains. We can see across vast distances, but we can't escape the fact that everything we see has already happened. We're perpetually out of sync with the universe, forever chasing a present that recedes before us at the speed of light. Imagine you're part of the first human colony on Proxima Centauri b, the planet orbiting our nearest stellar neighbor. You've made the journey somehow through some incredible advancement in technology, and now you're living on this alien world for 0.24 light years from Earth. You've built habitats, you're growing food, you're surviving, but you're also profoundly alone. Pause. You want to send a message back to Earth, to let them know you're okay, to share your discoveries, to ask for advice about a problem you're facing, so you compose your message and transmit it. The signal travels at the speed of light, the fastest possible speed in the universe. And after 4.24 years, it reaches Earth. They receive it. They craft a response. And they send it back. Another 4.24 years pass. If you're lucky, if everyone responds immediately, if there are no delays, you'll receive an answer in about 8.5 years. Pause. Think about what that means for decision making. If you face an emergency that requires expertise or resources from Earth, you can't call for help. By the time your distress signal reaches Earth, and help could theoretically arrive, the crisis will have long since resolved itself. One way or another, you're on your own. The colony must be completely self-sufficient, because the distance makes any form of meaningful real-time support impossible. Pause. And it's not just emergencies. It's everything. Cultural exchange, scientific collaboration, political coordination. All of it becomes asynchronous, delayed, fundamentally different from the instant global communication we're used to on Earth. You can't have a conversation. You can't argue in real time. You can't collaborate on a project. the way we do now, with video calls and shared documents. You send your piece. You wait years. You receive a response. That's addressing questions you asked years ago. Concerns you may have already resolved or forgotten about. Pause. Over time, this delay would create drift. The colony and Earth would develop differently, culturally and technologically. The people on Proxima Centauri b would be shaped by their environment, their challenges, their isolation. They develop their own traditions, their own ways of thinking, their own identity, separate from Earth. And Earth would continue evolving too, in its own direction. After a few generations, the two populations might have so little in common that the messages they exchange feel alien, hard to relate to. Pause. This isn't science fiction speculation. This is the mathematical reality of light-speed communication across light years. We're already experiencing a taste of it in our solar system. The Voyager 1 spacecraft, humanity's most distant emissary, is currently about 23 billion kilometers from Earth, about 1/5 of a light year. Commands sent to Voyager take more than 22 hours to reach it, and its responses take another 22 hours to return. A full conversation is nearly 2 days, just within our own solar system. Pause. When New Horizons flew past Pluto in 2015, it was so far away that the signal delay was about 4.5 hours each way. Mission Control sent commands hours before they were needed, trusting that the spacecraft would execute them correctly. When the time came, there was no room for real-time adjustments. If something went wrong, if a sudden course correction was needed, it would be too late by the time anyone on Earth knew about it. Pause. And Pluto is still within our solar system, still relatively close compared to the stars. Proxima Centauri is about 9,000 times farther away than Pluto. The communication challenges scale accordingly. Pause. Now imagine not a colony at Proxima, but an attempt to communicate with an alien civilization at TRAPPIST-1, 40 light years away. We sent a message. Hello. We are humanity. We come in peace. We would like to learn about you. 40 years later, if they happen to be listening, if they happen to be around the right radio frequencies, if they care enough to respond, our message arrives. Then they study it, debate what to say back, craft a response, Another 40 years. And we receive their reply. 80 years minimum. For a single exchange. The person who sent the original message would likely be dead before hearing a response. Entire generations might pass between question and answer. This isn't communication as we know it. It's more like time capsules. Messages launched into the future, hoping someone will find them and understand. Pause. And that assumes both civilizations exist for that entire duration. 80 years is a long time. Wars happen. Disasters strike. Civilizations fall. There's no guarantee that the Earth that receives a reply from TRAPPIST-1 would be in any position to understand or respond to it. There's no guarantee. The civilization on TRAPPIST-1 that responds would still be around to see our counter-response. Pause. The light speed limit doesn't just make space travel difficult. It makes communication across interstellar distances almost philosophically problematic. How do you build a relationship, a culture of exchange, when every interaction is separated by decades or centuries? How do you maintain interest, continuity, shared purpose, when the people involved keep changing, aging, dying? Pause. This is part of why the search for extraterrestrial intelligence, SETI, is both inspiring and deeply challenging. We're listening for signals from other civilizations, and we're sending some of our own. But even if we detect a signal tomorrow, even if we confirm it's from intelligent aliens, what then? We could learn about them. Yes. We could analyze their message, study their technology, marvel at the confirmation that we're not alone, but a conversation, a dialogue that might be beyond our reach, depending on how far away they are. Pause. If the signal comes from 50 light years away, it would take a century for them to receive our reply. 100 years, longer than most human lifespans, longer than most governments last, longer than most technologies remain relevant. We'd be sending messages to a civilization we can only hope will still exist and care by the time our words arrive. Pause. Yet despite all this, there's something noble in the attempt. There's something beautiful about the idea that we might reach across the light years across the void, across time itself, to touch another mind, another civilization, even if the conversation is painfully slow, even if it spans generations. It would still be a conversation. It would still be connection, however tenuous, however delayed. Pause. And maybe that's the point. Maybe communication across light years isn't about the immediate exchange of information. Maybe it's about persistence, about faith, about the long view. It's about recognizing that some things are worth doing, even if we won't live to see the results. It's about planting trees, under whose shade we'll never sit, sending messages we'll never see answered, reaching for stars we'll never touch. Pause. The light years defeat us. Yes. They impose delays we can't overcome, distances we can't cross quickly. But they don't silence us. We can still send signals. We can still listen. We can still try. And in that trying, in that refusal to accept isolation, maybe we find something essentially human. Hope in the face of impossible odds. Connection despite separation. Voices crying out into the darkness, not knowing if anyone will hear, but crying out nonetheless. Now we need to talk about something that makes cosmic distances even stranger, even more brain-breaking than they already are. We need to talk about time dilation, one of the most counterintuitive predictions of Einstein's special theory of relativity. Pause. You probably have an intuitive sense of how time works. It flows forward, steadily, 1 second per second. The same for everyone, everywhere. A minute is a minute, whether you're sitting still or flying in a jet. An hour is an hour, whether you're on Earth or on Mars. Time, in our everyday experience, is absolute. It's the background against which everything else happens. Pause. But Einstein discovered something extraordinary. Time is not absolute. It's relative. It depends on how fast you're moving. The faster you travel through space, the slower you move through time, relative to someone who's stationary. This isn't a trick or an illusion. It's a real, measurable, physical effect that has been confirmed through countless experiments. Pause. For example, atomic clocks on GPS satellites run slightly faster than identical clocks on Earth because they're moving at high speeds and experiencing slightly less gravity. The difference is tiny, measured in nanoseconds. But it's real, and it has to be accounted for, or GPS systems would quickly become inaccurate. Time literally runs at different rates for the satellites and for us on the ground. Pause. But these effects are tiny at everyday speeds. To see really dramatic time dilation, you need to travel at a significant fraction of the speed of light. And this is where things get weird. When we think about interstellar travel, pause. Imagine you somehow have a spacecraft that can accelerate to 99.5% of the speed of light. You decide to take a journey to a star system 40 light years away. From Earth's perspective, this journey takes a little over 40 years. You're traveling at nearly the speed of light. So you cover about 1 light year per year. Pause. But here's the thing. From your perspective on the spacecraft, time is running slower, much slower, at 99.5% of light speed. Time dilation becomes extreme. What feels like about 4 years for you is 40 years for Earth. You make the journey, turn around, and come back. For you, the round trip took maybe 8 years. You've aged 8 years. Your children are 8 years older than when you left. Pause. But when you return to Earth, 80 years have passed. Your children are elderly or dead. Your friends are gone. The world you left has transformed. Technologies have advanced. Societies have changed. You've been gone less than a decade from your own perspective, but you've traveled 80 years into Earth's future. Pause. This isn't science fiction. This is what Einstein's equations predict. And every test we've ever performed has confirmed these predictions. Time dilation is real. At high speeds, time slows down for the traveler relative to stationary observers. The closer you get to the speed of light, the more extreme the effect becomes. At 99.99% of light speed, time dilation is so severe that you could cross the entire galaxy 100,000 light years in what feels like just a few decades to you. Pause. To Earth, 100,000 years would have passed. Human civilization, as we know it, would be long gone. But for you, subjectively, it would have been a journey measured in years, not millennia. Pause. This creates A strange asymmetry. In interstellar travel, the distances are still vast. 40 light years is 40 light years. No way around that. But the experienced time for the traveler can be much less than the time elapsed for everyone else. You could explore the stars within your own lifetime, but you could never come home to the world you left. Every journey would be a one-way trip into the future. Pause. This is both a blessing and a curse. It means interstellar travel might be possible within a human lifespan for the travelers, but it also means that travelers become unstuck in time, disconnected from everyone and everything they left behind. Every journey is an exile. Every return, an arrival in a foreign future. Pause. There's also the question of what happens to the traveler during the journey at near light speeds. The universe looks different. Ahead of you, stars would appear blue shifted, their light compressed into higher energies. Behind you, stars would be red shifted, their light stretched out. The constellations would be distorted. If you traveled fast enough, you might even see the cosmic microwave background radiation, the leftover heat from the Big Bang, blue shifted into visible light. In front of you, pause. And then there's the problem of acceleration. To reach these high speeds, you need to accelerate. And acceleration means force. And force means stress on your body. If you accelerated too quickly, the G-forces would kill you. So you'd need to accelerate gently, gradually building up speed over weeks or months or years. And when you arrive, you'd need to decelerate just as carefully. The journey might take subjectively longer than the time dilation equations suggest, simply because you can't accelerate or decelerate instantaneously. Pause. But even accounting for all that, time dilation makes interstellar travel theoretically possible for individuals, even if it remains impractical. For civilizations, you could journey to the stars and return, but you'd return to a world that has moved on without you. You'd be a stranger in your own home. Pause. This is another way that light years break our brains. Not only are the distances vast, not only are we seeing the past, when we look at the stars. But time itself becomes flexible, variable, dependent on motion. The universe doesn't play by our intuitive rules. It's stranger, weirder, more wonderful than we could have imagined. Before Einstein, pause, and perhaps there's a poetry to this. Perhaps it's fitting that the faster we move, the slower we age. Perhaps it's the universe's way of saying that travel is always transformative, that journeys change us, that we can never truly go home, because home moves forward while we're away. Time dilation is physics, yes, but it's also metaphor, a reminder that motion and change are inseparable, that to move through space is also to move through time, and that the cosmos is far more interconnected and strange than our everyday experience suggests. Let's zoom out now. Let's leave our galaxy behind. Leave the nearby galaxies. Leave the local group. And try to comprehend the full scale of the cosmos. Pause. Let's talk about the observable universe. Everything we can, in principle, see. Pause. The universe is approximately 13.8 billion years old. We know this from multiple lines of evidence. The expansion rate of the universe, the cosmic microwave background radiation, the ages of the oldest stars, 13.8 billion years. Since the Big Bang, since the moment space and time came into existence, since the universe was an infinitesimally small, infinitely hot point that began expanding and has been expanding ever since. Pause. You might think, then, that the observable universe should be 13.8 billion light years in radius. After all, light has had 13.8 billion years to reach us, so we should be able to see things 13.8 billion light years away. Right. Pause. But that's not how it works. The universe has been expanding this whole time, and space itself is expanding, carrying galaxies away from each other. A galaxy that emitted light 13 billion years ago was much closer to us then. But during those 13 billion years, while the light was traveling toward us, the galaxy was being carried farther away by the expansion of space. By the time the light reaches us, that galaxy is now much, much farther away than 13 billion light years. Pause. When you account for this expansion, the actual size of the observable universe is about 93 billion light-years in diameter. That's the radius of the bubble of space, from which light has had time to reach us. Everything beyond that bubble is invisible to us, not because there's nothing there, but because the light from those regions hasn't had time to arrive yet. Pause. Within that 93 billion light-year sphere are approximately 2 trillion galaxies. 2 trillion. Each one contains tens of billions to hundreds of billions of stars. If you multiply it out, there are roughly 200 billion trillion stars in the observable universe. That's a 2, followed by 23 zeros. More stars than grains of sand on all the beaches of Earth. Pause. Every single one of those stars is a sun, potentially with planets, with moons, with asteroids and comets. Every single one is a place, a location in space, with its own history, its own story, and we can see them, or rather, we can see their past. Pause. The light from the most distant galaxies we've detected has been traveling for over 13 billion years. We're seeing those galaxies as they were when the universe was less than 1 billion years old, before the Milky Way even existed in its current form. Pause. These galaxies appear as faint smudges in our deepest telescope images, the Hubble Space Telescope's deep field images, and more recently, the James Webb Space Telescope's deep fields show us thousands of galaxies in tiny patches of sky. Each image captures billions of years of cosmic history, layer upon layer of light, from different eras, all arriving at our telescopes at the same moment, but originating from vastly different times. Pause. Looking at these images is like looking at a timeline of the universe. The closest galaxies are showing us the relatively recent past, maybe a few billion years ago. Farther out, we see galaxies from 5, 7, 10 billion years ago, and at the very edge of our vision, we see the earliest galaxies, the first structures to form after the Big Bang. Their light stretched and redshifted by the expansion of space until it's barely detectable. And here's something that should make you pause. All of this, all 93 billion light years of observable universe, all 2 trillion galaxies, this might just be a tiny fraction of the total universe. Pause. The actual universe, beyond what we can see, might be vastly larger. It might even be infinite. We don't know. We can't know. We're limited by the speed of light and the age of the universe. There could be entire regions of space, entire superclusters of galaxies, entire cosmic structures beyond our observable bubble that we will never, ever see, because their light will never reach us. Pause. In fact, due to the accelerating expansion of the universe, driven by something we call dark energy, there are galaxies we can see today that we'll never be able to reach, even if we could travel at the speed of light. The space between us and them is expanding faster than light can cross it. These galaxies are receding from us at faster than light speeds, not because they're moving through space faster than light, which is impossible, but because space itself is expanding. Pause. This means there's a cosmic horizon, a limit to what we can ever interact with. Galaxies beyond this horizon are essentially in a separate universe. As far as we're concerned, we might see their ancient light, but we can never visit them, can never communicate with them, can never influence them, or be influenced by them. They're beyond our reach, permanently and forever. Pause. And as time goes on, as the universe continues to expand and accelerate, this horizon will shrink. Galaxies that are currently visible will eventually recede beyond the horizon and disappear from view. In trillions of years, the sky will be much emptier than it is now. Future observers, if they exist, will see only their local group of gravitationally bound galaxies. Everything else will have been carried away by expansion, leaving them in an island universe, isolated, with no evidence that the larger cosmos even exists. Pause. But that's a concern for the far future. Right now, right here, we live in a golden age of astronomy. We can see almost the entire history of the universe spread out across the sky. We can trace the evolution of galaxies, watch stars being born and dying, observe the large-scale structure of the cosmos. We're living in a time when the universe is visible, when the evidence of our cosmic origins is all around us, written in the light from distant stars and galaxies. Pause. And when you look up at the night sky, you're participating in this. You're gathering photons that have traveled for years, centuries, millennia, billions of years. To reach you, you're seeing light from so far away that the distances become absurd, meaningless, incomprehensible, but you're seeing it nonetheless. You're connected to all of it. Every star, every galaxy, every distant corner of the observable universe. Through the medium of light. Pause. We are, in a very real sense, at the center of the observable universe. Not because we're special, but because observable universe is defined relative to the observer. Wherever you are, you're at the center of your own observable universe, a 93 billion light-year sphere, with you at its heart, an alien on a planet, in a distant galaxy, would have their own observable universe, overlapping with ours in some regions, extending into different regions in others. Pause. This is the scale we're dealing with. This is what light years mean when extended to cosmic distances. The universe is so large that light, traveling at the ultimate speed limit, still takes billions of years to cross it. It's so large that despite containing trillions of galaxies, it might still be just a speck in a larger, possibly infinite reality. Pause. And yet, we're here, small specks on a small planet, orbiting a medium star, in one galaxy among trillions, looking out and trying to understand it all. That's either the ultimate cosmic joke or the ultimate cosmic miracle, depending on how you look at it. The universe isn't uniformly distributed. If you zoom out far enough, you start to see structure, patterns, organization on scales that dwarf galaxies. Galaxies tend to cluster together, drawn by their mutual gravitational attraction. Our Milky Way is part of the local group, which includes Andromeda and about 50 smaller galaxies. But the local group is just one small cluster among many. Zoom out more, and you see that galaxy groups and clusters themselves cluster into superclusters. The local group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters. The Virgo cluster, at the heart of this supercluster, contains over 1,000 galaxies. It's about 54 million light years away, meaning the light we see from it today left when early primates were evolving on Earth. But even superclusters are part of larger structures. Recent mapping has revealed that superclusters are organized into vast filaments and sheets, with enormous voids between them. These cosmic filaments can stretch for hundreds of millions of light years, containing thousands of galaxies, all aligned in vast, thread-like structures. And between the filaments are the voids, vast, mostly empty regions of space, where very few galaxies exist. These voids can be hundreds of millions of light years across, enormous bubbles of near emptiness. The largest known void, the Boötes Void, is about 330 million light years in diameter and contains very few galaxies. If the Milky Way were in the center of such a void, we wouldn't have discovered other galaxies until the 1960s. The sky would have been almost empty of external galaxies, which would have given us a very different view of the universe. This structure, filaments, sheets, clusters, and voids, is sometimes called the cosmic web. It's the largest structure in the universe, and it formed through gravity, acting on tiny density fluctuations. In the early universe, regions that were slightly denser than average attracted more matter, becoming even denser, while regions that were slightly less dense had matter flow out of them, becoming voids. The cosmic web is dynamic too. Galaxies are moving along these filaments, falling toward the densest regions. Galaxy clusters are colliding and merging. The structure is evolving over cosmic time. A map of the cosmic web today looks different from what it would have looked like 10 billion years ago, or what it will look like 10 billion years from now. And undergirding all of this, driving the expansion and evolution of the universe, is something mysterious. Dark energy. In the 1990s, astronomers made a shocking discovery. By studying distant supernovae, exploding stars that can be used as standard candles to measure cosmic distances, they found that the expansion of the universe is accelerating, not slowing down, as you'd expect if gravity was the dominant force, but speeding up. This shouldn't be possible. Gravity is attractive. It should be pulling galaxies together, slowing the expansion. But something is pushing space apart. Some form of energy that permeates all of space and drives expansion. We call it dark energy because we don't know what it is. It doesn't emit light, doesn't interact with matter in any way we can detect, except through its gravitational effects on the cosmos as a whole. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, the stuff stars and planets and people are made of, is less than 5%. We're made of the universe's rarest ingredient. The accelerating expansion, driven by dark energy, has profound implications for the future. If it continues, and we have no reason to think it won't, the universe will expand forever. Galaxies will recede from each other at ever-increasing speeds, and eventually, in the deep future, the sky will be empty. Every galaxy beyond our local group will have been carried beyond the horizon, their light redshifted into undetectability. In that far future, beings like us would look up and see only the stars of their own galaxy and its gravitationally bound neighbors. They would have no evidence that billions of other galaxies exist. The cosmic microwave background radiation would have been redshifted beyond detection. They would have no way to know that the universe had a beginning, that there was a Big Bang. Their universe would appear static, eternal, and isolated. But for now, we can see the cosmic web. We can trace the filaments and voids. We can measure the expansion rate and the acceleration. We can detect the cosmic microwave background and study the early universe. We live in an era when the cosmos is visible, when its history is written in the light from distant galaxies. And the light years, they're the threads that connect it all. Every filament of the cosmic web is hundreds of millions of light years long. The distance between galaxy clusters is tens of millions of light years. The distance to the most distant galaxies is billions of light years. These distances are so vast that the light we see from these structures is ancient, showing us not how they are, but how they were. When we map the cosmic web, we're mapping the past. The nearby structures show us the recent past. A few million or tens of millions of years ago, the distant structures show us billions of years ago. We're constructing a timeline, a history of the universe, from the light that's been traveling across space. All this time, and space itself, the stage on which all this plays out, is expanding, not into anything. There's no outside of space for it to expand into. Space itself is growing, stretching, carrying galaxies along with it. The light years are getting longer. The distance is increasing. The universe becoming more vast and more empty with each passing moment. This is the cosmos at its largest scales. This is the arena in which galaxies and clusters and superclusters play out their gravitational dances. This is the universe that light years measure, the distances they span, the time they encode, and we, on our small planet, can see it all. We can trace the cosmic web, measure the expansion, probe the nature of dark energy and dark matter. We can look out across billions of light years and billions of years of time and piece together the story of how we got here, how the universe evolved from a hot, dense state to the vast, structured cosmos we inhabit today. It's humbling. Yes, it makes us small, but it's also empowering. We're small, but we're capable of understanding the large. We're brief, but we're capable of comprehending the ancient. We're made of ordinary matter, a tiny fraction of the universe's content, but we're able to deduce the existence of the dark components that dominated. Light years give us the scale, the context, the framework for all of this. And in crossing those light years, with our telescopes and our minds, we connect ourselves to the cosmos, making the distant near, the ancient present, the vast comprehensible. Now we come to one of the most profound questions in all of science, a question that light years make both more pressing and more poignant. Where are the aliens? The logic seems straightforward. Our galaxy contains roughly 200 to 400 billion stars. Many, perhaps most, of those stars have planets. We've confirmed thousands of exoplanets, and estimates suggest there are tens of billions of potentially habitable worlds. In the Milky Way alone, life arose on Earth relatively quickly after the planet formed, suggesting that the emergence of life might not be that difficult, given the right conditions. And Earth is young. Our Sun is a middle-aged star. But there are stars in the galaxy that are billions of years older. There are planets out there that could have had billions of years more time for life to evolve, civilizations to develop, technology to advance. By all rights, the galaxy should be teeming with intelligent life, many of them far more advanced than we are. So where are they? Where are the radio signals? The evidence of megastructures? The visitors? The signs of intelligence? Why does the galaxy seem so quiet? This is the Fermi Paradox, named after physicist Enrico Fermi, who reportedly asked this question over lunch one day. Where is everybody? There are many proposed solutions to the paradox, but one aspect that's often overlooked is the sheer scale involved. The Milky Way is 100,000 light years across. Even if civilizations exist, even if they're common, the distances between them might be so vast that contact is essentially impossible. Consider our own efforts to communicate. We've been broadcasting radio signals into space for about a century now. Those signals are traveling outward at the speed of light, forming a bubble about 100 light years in radius around Earth. That bubble contains maybe a few thousand stars. Compared to the 400 billion stars in the galaxy, we've reached almost nobody. And even within that bubble, our signals are weak. They diminish with distance, spreading out and becoming fainter. By the time they reach even the nearest stars, they're barely distinguishable from background noise. An alien civilization would need very sensitive equipment and would need to be specifically looking in our direction at the right frequencies to detect us. Now imagine the reverse. If there's an alien civilization 1,000 light years away, broadcasting signals just like we are, we wouldn't have received them yet, unless they started broadcasting before the early Middle Ages. And if they're 10,000 light years away, their signals left when humans were still in the Stone Age, building the first agricultural settlements. The galaxy might be full of civilizations, all broadcasting, all listening, but none of them able to hear each other, because the signals haven't had time to arrive yet. We might be living in a galaxy of voices, calling out into the darkness, none of them aware of the others, because the distances are just too vast, and the speed of light too limiting. Or perhaps civilizations are common, but short-lived. Maybe intelligent species tend to destroy themselves through war, environmental collapse, resource depletion, or some other catastrophe before they develop the technology to spread beyond their home planet or to communicate across interstellar distances. In that case, the galaxy might be full of ruins, failed experiments in intelligence, civilizations that flickered briefly and then went dark. If the typical lifespan of a technological civilization is only a few hundred years, and they're scattered across the galaxy, the chances of two civilizations existing at the same time and close enough to communicate are very small. We might be surrounded by the graveyards of alien worlds, planets where intelligence arose and vanished before we even existed. There's also the possibility that we're just early. The universe is 13.8 billion years old, but the first few billion years were too chaotic, too metal poor, to support the chemistry needed for life as we know it. Stars needed to form, live out their lives, and die, enriching space with heavier elements before planets like Earth could form. Maybe the universe is only now becoming truly habitable, and we're among the first civilizations to arise. We're not latecomers to a crowded party. We're early arrivals to an event that's just beginning. Or maybe intelligence is rare. Maybe the path from simple life to complex technological civilization involves so many unlikely steps, so many bottlenecks and filters, that only a tiny fraction of planets ever produce beings capable of asking, "Where is everybody?" Maybe we're one of the lucky few, or even the only ones. Each of these explanations has implications, and light years amplify all of them. If civilizations destroy themselves before spreading, the light years ensure we'll never know they existed, unless they're very close. If we're early, the light years mean we're looking out at a galaxy that might be full of potential, but is currently empty. If intelligence is rare, the light years mean the few civilizations that do exist are so far apart, they'll never find each other. And even if we do detect a signal, even if we confirm that we're not alone, what then? If the signal comes from 5,000 light years away, any response we send will take 5,000 years to reach them, and their reply another 5,000 years to return. 10,000 years for a single exchange, longer than all of recorded human history. By the time we receive their reply, human civilization might have changed beyond recognition. We might not even care about the question we asked 10,000 years ago, or we might not exist at all. 10,000 years is a long time. For a species, for a civilization, for continuity, the light years that make the universe observable also make it lonely. They let us see countless stars and galaxies, but they keep us isolated from them. They let us wonder about life elsewhere, but they made contact difficult or impossible. They connect us to the cosmos through light, but they separate us from it through time and distance. Maybe the Fermi Paradox isn't really a paradox at all. Maybe it's just the reality of a universe where light speed is the limit and space is vast. Maybe the galaxy is full of life, full of civilizations, full of beings asking the same questions we are. But the distances are too great, the timescales too long, the speed of light too slow. Or maybe we are alone. Maybe the silence is real. Maybe we're the first, or the last, or the only. And if that's true, if we're the universe's only experiment in consciousness, then we carry an incredible responsibility. We're the universe's eyes and ears. The only way it has to know itself, to appreciate its own beauty, to ask questions about its own nature. Either way, whether we're one among many, or the only one, light years define our situation. They give us the scale of our isolation, the measure of our separation, the scope of our loneliness, and they remind us that in this vast cosmos, the fact that we're here at all, able to ask these questions, able to look up and wonder, is something rare and precious and worth preserving. So we've established that the distances between stars are vast, measured in light years, making them difficult to cross. But is interstellar travel actually possible? Could humans ever visit other star systems? Or are we forever confined to our cosmic neighborhood? Let's start with the brutal reality of our current technology. The fastest spacecraft we've ever built is the Parker Solar Probe, which at its peak reaches speeds of about 700,000 kilometers per hour. That sounds incredibly fast, and it is, by human standards. But let's put it in perspective. At that speed, it would take about 6,000 years to reach Proxima Centauri, our nearest stellar neighbor, at 4.2 light years away. 6,000 years. That's longer than all of recorded human civilization. That's longer than agriculture has existed. A spacecraft launched today wouldn't arrive until the year 800 AD, assuming it could maintain that speed, which it can't, without constant propulsion. To make interstellar travel feasible within a human lifetime, we'd need to achieve a significant fraction of the speed of light. Let's say 10% of light speed, which would allow us to reach Proxima Centauri in about 42 years. Still a long time, but within a human lifespan. But achieving 10% of light speed is enormously difficult. It requires vast amounts of energy to accelerate a spacecraft to that velocity. Using conventional chemical rockets would require more fuel than exists on Earth. It's simply not feasible with our current propulsion technology. Alternative propulsion methods have been proposed. Ion drives, which accelerate particles using electric fields, are more efficient than chemical rockets, but they produce very little thrust. It would take years of continuous acceleration to reach high speeds. Solar sails, pushed by the pressure of sunlight, could theoretically achieve high velocities without carrying fuel, but they would need to be enormous, kilometers across, and would only work well within the inner solar system, where sunlight is strong. More exotic ideas include nuclear pulse propulsion, detonating nuclear bombs behind the spacecraft to push it forward, Antimatter rockets. Using matter-antimatter annihilation for propulsion, or even theoretical concepts like warp drives. That would bend space itself. But these range from technically challenging to currently impossible with our understanding of physics. Even if we solve the propulsion problem, there are other challenges. At high speeds, even tiny particles become dangerous. A grain of dust hitting a spacecraft, traveling at 10% of light speed, would impact with the energy of a bomb. The spacecraft would need shielding, which adds mass, which requires more energy to accelerate. Then there's radiation. Space is filled with cosmic rays, high-energy particles from various sources that can damage both equipment and living tissue. Earth's magnetic field and atmosphere protect us. But in interstellar space, there's no protection. Long-duration space travelers would be exposed to radiation that could cause cancer, damage their DNA, harm their nervous systems. Life support is another issue. Humans need air, water, food, waste recycling, temperature control, protection from radiation. All of this requires mass and energy. For a journey lasting decades, you'd need either an extremely efficient recycling system or vast stores of supplies. Either way, it adds to the mass of the spacecraft, which requires more energy to accelerate. And then there's the psychological aspect. Spending decades in a small spacecraft, isolated from Earth, knowing you can never turn back, knowing everyone you knew is aging or dying while you're gone. It would be mentally challenging, to put it mildly. Depression, anxiety, interpersonal conflicts among the crew, the loss of purpose. All of these would be risks. On such a long journey, one proposed solution is the generation ship, a massive spacecraft designed to house not just the initial crew, but their descendants as well. The idea is that the first generation boards the ship. They live out their lives aboard it, have children, and those children continue the journey. Eventually, after several generations, the ship arrives at its destination, and the descendants of the original crew colonize the new world. But generation ships have their own problems. How do you maintain social cohesion across generations? How do you preserve the mission's purpose when the people arriving have never known Earth and have only heard stories from their grandparents? How do you deal with genetic bottlenecks from a small population? How do you maintain the ship systems for centuries? Another idea is cryogenic sleep, freezing the crew for the duration of the journey. and waking them up when they arrive. This is a staple of science fiction, but we're nowhere near being able to do it in reality. We can freeze and revive simple organisms like tardigrades, and we can preserve cells and tissues. But freezing and reviving a whole human without damage, that's currently beyond our capabilities. Even if we solve all these problems, even if we build a spacecraft capable of reaching 10% of light speed, capable of protecting its occupants, capable of sustaining them for decades, there's still the question of why. Why undertake such an expensive, dangerous, difficult journey? Scientific knowledge. Perhaps the chance to study an alien star system up close, to examine exoplanets in detail, to search for life on other worlds. There's value in that. Certainly. Or perhaps survival. If Earth becomes uninhabitable, whether through environmental collapse, nuclear war, asteroid impact, or some other catastrophe, having colonies on other worlds would ensure the survival of our species. We'd become a multi-world civilization, resilient to single-point failures. Or maybe it's something deeper. Maybe it's the same drive that led humans to cross oceans, to climb mountains, to explore Antarctica, to go to the moon, the desire to see what's out there, to expand our horizons, to push the boundaries of what's possible. Maybe we go to the stars for the same reason we've always explored, because they're there. But realistically, with our current technology and our current understanding of physics, interstellar travel is beyond our reach. We can send robotic probes, maybe tiny spacecraft accelerated by powerful lasers, reaching fractional light speeds, arriving at nearby stars, and sending back data. That might be feasible in the coming decades or centuries. But human travel, that's much harder. It might require breakthroughs in physics we haven't made yet, technologies we haven't invented, an understanding of the universe we don't currently possess. And yet, 600 years ago, crossing the Atlantic was a monumental undertaking. 200 years ago, crossing continents was difficult and dangerous. 100 years ago, flight was a novelty. 50 years ago, going to the moon was science fiction. Technology advances. Understanding deepens. What seems impossible today might be routine tomorrow. Maybe our descendants will look back at our caution about interstellar travel the way we look back at people who thought flying machines were impossible. Or maybe the light years really are a barrier we can't overcome. Maybe the universe is designed to keep civilizations isolated, each confined to their own little island in space, able to see each other, but never to touch, forever separated by distances too vast to cross. Either way, the dream remains. The stars call to us. Light years measure the distance, but they don't diminish the desire to reach out, to explore, to go where no one has gone before. Even if we never make it, even if the dream remains forever unfulfilled, there's value in dreaming, in reaching, in trying, because that's what makes us human. Not our ability to achieve the impossible, but our refusal to accept limits, our insistence on dreaming of the stars, even when we're bound to the earth. Let's bring together everything we've discussed and ask the ultimate question: could we ever actually meet an alien civilization? Not just detect their signals, not just know they exist, but actually meet them, communicate with them in any meaningful way. The honest answer, given what we understand about physics and the cosmos, is that it's extremely unlikely, bordering on impossible, and the primary reason is light years. Imagine we detect a signal tomorrow from an alien civilization. The signal is clear, unmistakable, obviously intelligent in origin. It's the confirmation we've been waiting for. We're not alone. Humanity celebrates. We've answered one of our deepest questions. But then reality sets in. Where did this signal come from? Let's say it's from a civilization 100 light years away. That signal was sent 100 years ago, in the early 1920s by Earth time. The civilization that sent it, are they even still around? 100 years is a long time. They could have been wiped out by a war, a plague, an environmental disaster, or they could have advanced beyond recognition, or lost interest in communicating, or moved elsewhere. We decide to send a response anyway. We craft a message, and code it with information about Earth, about humanity, about our mathematics and science and culture, and we broadcast it toward their location. That message will take 100 years to reach them. If they still exist, if they're still listening, if they receive it and decide to respond, their reply will take another 100 years to reach us. 200 years for a single exchange of messages. In the year 2226, humanity might receive a reply to the message we send today. What will the world be like then? Will the people who receive the reply even remember that we sent the original message? Will they care? And that's assuming the civilization is only 100 light years away. If they're 1,000 light years distant, A single exchange would take 2,000 years. If they're across the galaxy, 50,000 light years away, an exchange would take 100,000 years. Longer than modern humans have existed. This makes conversation impossible. We could exchange information. Yes. They could tell us about their science, their culture, their history, and we could do the same. But it wouldn't be a dialogue. It would be more like letters between generations. Messages passed down through vast spans of time. And what about actual physical meetings? Could we ever travel to meet them? Or they to meet us? With our current technology? Absolutely not. Even if we could build a spacecraft capable of reaching 10% of light speed, which we can't. A journey to a civilization 100 light years away would take 1,000 years. The people who arrived would be the distant descendants of those who left, generations removed from Earth. And the energy requirements for such a journey would be staggering. The faster you want to go, the more energy you need, and the amount increases exponentially as you approach the speed of light. To accelerate even a small spacecraft to half the speed of light would require more energy than humanity currently produces in years. There's also the problem of deceleration. If you accelerate to high speeds for the journey, you need to decelerate when you arrive, which requires just as much energy. So you need to carry enough fuel or have enough energy generation capability, not just to accelerate, but to slow down again. The mass and energy requirements become prohibitive. Some have proposed using laser propulsion, giant laser arrays on Earth or in orbit, pushing light sails on spacecraft to accelerate them to high speeds. This could work for tiny probes, but not for crewed missions. The probes couldn't carry humans, and they couldn't slow down when they arrived. There's no laser at the other end to decelerate them. They'd be flyby missions, zipping past at a fraction of light speed, gathering data for a brief moment, then continuing on into the void. Even if aliens exist, even if they're common, even if the galaxy is teeming with civilizations, the chances of us ever meeting any of them are vanishingly small. The distances are too vast, the energy requirements too high, the timescales too long. But perhaps meeting doesn't have to mean physical presence. Perhaps it means exchange of information, sharing of knowledge, even if delayed by centuries or millennia. Perhaps it means knowing we're not alone, even if we're forever separate. And maybe that's enough. Maybe the knowledge that intelligence exists elsewhere, that life has found a way on other worlds, that there are other minds pondering the same questions we are. Maybe that's meaningful. even without direct contact. Or maybe it's tragic. Maybe it's the ultimate loneliness. To know others exist, but to be forever unable to reach them. To be able to see them, but not touch them. To be able to call out, but to wait lifetimes for an answer. The light years give us the cosmos, but they also take it away. They let us see, but not reach. They connect us to the universe through light, but they isolate us through time and distance. They're both bridge and barrier, window and wall. If there are aliens out there, and statistically, it seems likely there are, they're probably facing the same challenges we are. They're probably looking up at their own skies, seeing the light from distant stars, calculating the vast distances involved, and coming to the same conclusion. The universe is beautiful, vast, full of potential life, and yet each civilization is alone, isolated by the simple fact that space is big and light is slow. Perhaps that's the universe's greatest paradox. It's large enough to contain countless worlds, countless minds, countless civilizations, and yet the very largeness that allows for this diversity also ensures that each civilization is alone, looking out at others, but unable to truly connect. Or perhaps we're missing something. Perhaps there are ways around the light speed limit we haven't discovered. Perhaps advanced civilizations have technologies we can't imagine. Perhaps somewhere out there, beings are crossing the light years, visiting other worlds, building a galactic community. But based on what we know now, based on our current understanding of physics, the light years are a barrier we can't overcome. We can dream of the stars. We can send signals into the void. We can search for signs of others. But we probably can't cross the distances that separate us. And so we remain here, on our pale blue dot, looking up at the night sky, seeing the light from distant stars and galaxies, knowing that somewhere out there, perhaps, others are looking up too, seeing our sun as just another point of light, wondering if anyone is out there, wondering if they're alone. We're connected through the same questions, the same curiosity, the same sense of wonder, but we're separated by light years, by distances that defeat even imagination, by time delays that outlast civilizations. Perhaps that's the human condition writ large. To be connected and yet separate. To be part of something vast, and yet alone in our corner of it. To be able to see, and yet not touch. To know, and yet not reach. The light years tell us we're part of a cosmos vast beyond comprehension. But they also tell us we're on our own, and maybe learning to live with that paradox. To feel both connected and alone, both significant and insignificant, is what it means to be a conscious being in this strange and beautiful universe. Let's step back for a moment from the science, from the numbers and the physics, and think about what all of this means for us. What do light years teach us about our place in the universe? First, they teach us about scale. We live our lives in meters and kilometers, in minutes and hours. We think about distances we can walk, drives we can make, flights we can take. The farthest most people ever get from their birthplace is a few thousand kilometers. The longest journey most people take is measured in hours or days. But the universe operates on scales that dwarf our everyday experience. Light years measure distances of trillions of kilometers. The cosmic timescale is billions of years. The nearest star is so far away that light, the fastest thing in existence, takes over 4 years to reach it. The galaxy is so large that light takes 100,000 years to cross it. We are small, unimaginably, incomprehensibly small. Earth is a tiny rock, orbiting an average star, in an unremarkable region of a galaxy. That's one of trillions. If you could zoom out far enough to see the whole observable universe, Earth wouldn't be visible. The solar system wouldn't be visible. The Milky Way would be a single pixel, if that. Carl Sagan called Earth a pale blue dot, based on a photograph taken by Voyager 1 from the edge of the solar system, where Earth appears as a tiny speck of light, barely distinguishable from the void around it. That's all we are, on the cosmic scale, a dot. And all of human history, all our wars and achievements and civilizations, all our love and hate and dreams, all of it has played out on that dot. It's humbling. It puts our problems in perspective. The things we worry about, our jobs, our relationships, our social status, they're significant to us. Yes, but on the cosmic scale, they're infinitesimal. The entire span of human existence is a blink of an eye compared to the age of the universe. If the universe's history were compressed into a single year, human civilization would occupy the last few seconds before midnight on December 31 ST. But here's the paradox. While we're small, we're also significant in a different way. As far as we know, we're the universe's only way to know itself. We're the only beings in our corner of the cosmos, capable of looking up at the stars, and understanding what we're seeing, capable of measuring the distances and calculating the timescales, capable of feeling wonder and asking why. The universe is vast. Yes, but it's mostly empty. Most of it is vacuum, dark and cold and lifeless. Stars are rare. Planets are rarer. Life is rarer still. Intelligence, possibly extremely rare, possibly unique to us, though we don't know. And that makes us precious, not in a cosmic sense. The universe doesn't care about us. It's not even aware of us in any meaningful way, but in the sense that consciousness might be incredibly rare, that the ability to think and wonder and create might be a unique emergent property of certain complex arrangements of matter, and we're one of the few, or perhaps the only, examples of it. We're stardust. Yes, the atoms in our bodies were forged in the cores of dying stars. Billions of years ago, we're made of the same stuff as the planets and the stars, but we're stardust that can think about its own origins, that can trace its lineage back to the Big Bang, that can understand the nuclear fusion processes that created the elements we're made of. That's remarkable. Out of the chaos and randomness of the universe, out of the simple laws of physics, playing out over billions of years, emerged complexity, then life, then consciousness, and that consciousness can now look back at the universe that created it and comprehend it, at least partially. Light years teach us this. We're small in scale, but potentially large in significance. We're brief in duration, but rich in experience. We're isolated in space, but connected to everything through our shared origins. They also teach us about time. When you look at the stars, you're not seeing the present. You're seeing the past. Every photon that reaches your eye is old, carrying information about events that happened years, or centuries, or millennia ago. The night sky is a museum of history, and you're walking through it. Every time you look up, this means that the universe you observe is not the universe as it is, but the universe as it was. The present exists only here, only now, only in your immediate vicinity. Everything else is memory, encoded in light, traveling across the void. And this has philosophical implications. It suggests that now is a local phenomenon. That simultaneity breaks down at cosmic distances. That the universe doesn't have a universal present moment. Different observers in different locations will have different nows, different presents, that don't align. Einstein taught us this with relativity. Time is not absolute. It's relative to the observer, dependent on velocity and gravity. At cosmic scales, this becomes even more pronounced. The universe is not a static stage on which events play out. It's dynamic, with time itself being flexible and variable. Light years embody this. They're a measurement of distance. Yes, but they're also a measurement of time. They bind space and time together, making them inseparable. In doing so, they remind us that the universe is stranger than our intuition suggests, that our everyday experience of time as a steady, uniform flow is just an approximation that breaks down at extreme scales. And perhaps there's a lesson in that. Perhaps light years are teaching us to be humble, to recognize that our intuitions are limited, that the universe is under no obligation to make sense to us. That reality is what it is, regardless of whether we can easily comprehend it. They're also teaching us about loneliness. The vast distances between stars mean that if there are other civilizations out there, we're separated from them by barriers we may never overcome. We might see each other, might detect each other's signals, might confirm each other's existence, but we might never meet, never communicate in real time, never truly connect. And even if we're alone, if we're the only intelligence in the galaxy, or even in the universe, the loneliness remains. We're isolated on this pale blue dot, surrounded by vast emptiness, with no one to talk to but ourselves. But maybe loneliness isn't the right word. Maybe solitude is better. Solitude can be peaceful, contemplative, an opportunity for introspection. Maybe being alone in the cosmos gives us the space to figure out who we are, what we value, what we want to become, without outside interference. Or maybe the point isn't about being alone or together. Maybe the point is about the journey, the search, the reaching out, even when we don't expect to find anyone. Maybe it's about the act of looking up at the stars and wondering, regardless of whether we ever get an answer. Light years measure the distances we can't cross, but they also inspire us to try. They show us worlds we can't reach, but they make us want to reach them anyway. They define our limitations, but they also challenge us to overcome those limitations. And in that challenge, in that reaching, in that refusal to accept that the stars are forever out of reach, we find something essentially human. We find curiosity, wonder, determination, hope, we find the drive that led us out of Africa, across the oceans, to the moon, and perhaps, someday, to the stars. Light years break our brains because they force us to confront scales we didn't evolve to understand. But in breaking our brains, they also expand them. They stretch our thinking, push our imaginations, force us to grapple with concepts that are difficult and strange and beautiful. And maybe that's the real gift of light years. Not that they measure the universe, but that they challenge us to comprehend it. Not that they show us how far away things are, but that they inspire us to imagine the journey anyway. We're small. Yes. We're brief. Yes. We're isolated. Yes. But we're also curious, creative, conscious. We can look at light years and understand what they mean. We can measure cosmic distances and timescales. We can trace the history of the universe and our place in it. That's not nothing. That's extraordinary. And maybe, just maybe, it's enough. So here we are, at the end of our journey through space and time, having traveled from the moon to the edge of the observable universe, from seconds to billions of years, from the familiar to the incomprehensible. We've learned what light years are. Not just a unit of distance, but a binding of space and time. A measurement that forces us to think about the universe in new ways. We've learned that when we look at the stars, we're looking at the past. That the night sky is a museum of cosmic history. That now is a local phenomenon. And the present exists only here. We've toured our stellar neighborhood, visited exoplanets, contemplated the structure of our galaxy, and the larger cosmos beyond. We've grappled with the Fermi Paradox and the challenges of interstellar communication and travel. We've confronted Einstein's relativity and the strange effects of time dilation. We've zoomed out to see the observable universe in all its vastness, and we've zoomed back in to ask what it all means for us. And through it all, light years have been our guide and our challenge. They've given us the scale of the cosmos, but they've also shown us our limitations. They've connected us to distant stars and galaxies, but they've also isolated us. They've answered some questions and raised others. They've expanded our understanding and humbled us at the same time. Every time you look up at the night sky, you're participating in this cosmic story. You're gathering photons that have traveled for years, centuries, millennia. You're seeing the past, spread out across the heavens, layer upon layer of history, all visible at once. You're connecting to stars that might not even exist anymore, galaxies that have evolved into something different, structures that have changed beyond recognition. You're also seeing your own history. The light from Sirius left when you were younger. The light from Polaris left when your ancestors were building civilizations. The light from distant galaxies left before Earth even existed, before the sun had formed, before our corner of the universe was anything more than a cloud of hydrogen and helium. And in a very real sense, you're seeing yourself. The atoms in your body were created in the cores of long-dead stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stellar furnaces and scattered into space when those stars died. You are, quite literally, made of stardust. This is what light years teach us. We're connected to the cosmos in ways both profound and humbling. We're part of a story that began 13.8 billion years ago and continues into an uncertain future. We're made of the universe's material, shaped by its laws, brief participants in its unfolding drama. But we're also observers, understanders, meaning makers. We're the universe's way of knowing itself, of appreciating its own beauty, of asking questions about its own nature. And that makes us special. Even if we're small, that makes us significant. Even if we're brief, light years remind us of how connected and yet how separated we are from everything else. They show us countless stars and galaxies, but they keep them out of reach. They let us see, but not touch. They inspire us to reach for the stars, even as they demonstrate how far away those stars really are. And maybe that's okay. Maybe the reaching is more important than the arriving. Maybe the questions matter more than the answers. Maybe the journey itself, the act of exploring and discovering and understanding, is the point. When our ancient ancestors looked up at the stars, they saw gods and heroes, patterns and stories. They didn't know about light years, or galaxies, or the expanding universe. They didn't know that the stars were other suns, impossibly far away, or that the light they were seeing had been traveling for years or centuries. But they felt the same wonder we do. They felt the same awe, the same curiosity, the same desire to understand. That feeling, that sense of being part of something larger than ourselves, that impulse to look up and ask why, that's timeless. It transcends light years. It connects us to every human who has ever gazed at the night sky and wondered? And now we know so much more. We know what the stars are. We know how far away they are. We know about exoplanets and black holes and cosmic expansion. We've measured the universe, traced its history, predicted its future. We've solved mysteries that our ancestors couldn't even formulate. But in solving those mysteries, we've uncovered deeper ones. Every answer leads to new questions. Every discovery reveals new horizons. The more we learn, the more we realize how much we don't know. Light years embody this. They're a measurement we understand, but they point to scales we struggle to comprehend. They're familiar and yet strange, knowable and yet overwhelming, a bridge between the human and the cosmic. So the next time you're out at night, far from city lights, and you see the Milky Way stretching across the sky, remember what you're looking at. You're seeing hundreds of billions of stars, most of them with their own planets, each one a sun to someone or something, each one a story written in light and time. You're seeing photons that have traveled for thousands of years to reach your eyes. You're seeing the past, the history of the galaxy, the archive of cosmic time. You're seeing distances so vast that even light, the fastest thing in existence, takes years or centuries or millennia to cross them. And you're seeing yourself reflected in all of it. Because you're made of the same stuff as those stars. You're governed by the same laws of physics. You're part of the same cosmic dance, the same universal story that began with the Big Bang and continues to this moment. Light years measure the distance between here and there, between now and then, between us and the cosmos. But they also measure the connection, the relationship, the fundamental unity of all things. In measuring how far apart we are from the stars, they also show how deeply we're connected to them. And maybe that's the final lesson. Maybe light years teach us that distance and connection aren't opposites. Maybe they're two aspects of the same thing, two ways of understanding our relationship to the universe. We're separated by vast distances, yes, but we're also connected through light, through physics, through our shared origins in the primordial cosmos. We're alone, but we're part of something vast. We're small, but we're significant. We're brief, but we're connected to the eternal. We're isolated by light years, but we're also defined by them, inspired by them, challenged and humbled and uplifted by them. This is what breaks our brains, the simultaneous recognition that we're insignificant and irreplaceable, isolated and connected, tiny and vast, brief and eternal. Light years force us to hold these contradictions in our minds, to accept that the universe is complex and strange and doesn't fit neatly into our categories of understanding. But in that breaking, in that struggle to comprehend, we find something precious. We find growth, expansion, transcendence. We find the edges of our understanding and push against them. We find the limits of human knowledge and dare to go beyond. Every photon that reaches your eye tonight carries a message from the past, from across light years of space, from stars and galaxies and cosmic structures. That message says, the universe is vast, and you are small, but you are here, and you can see this, and you can understand it, and that is miraculous. Listen to that message. Feel it. Let it change you. Let the light years break your brain and rebuild it into something larger, something more capable of wonder, something more attuned to the cosmic symphony playing out across space and time. We are stardust looking back at the stars. We are the universe contemplating itself. And we are connected to it all, every atom, every star, every galaxy, through the light that travels across the years, carrying stories from the depths of space and time. That connection, measured in light years, is our birthright and our burden, our limitation and our liberation, the thing that isolates us and the thing that makes us part of something infinite. So look up. See the stars. Remember that you're seeing the past. And know that you're part of it all, this vast, strange, beautiful cosmos that gave birth to you and will outlast you, but will carry your atoms forward into whatever comes next. Light years measure the distance to the stars. But they also measure the distance we've come in understanding, the distance we still have to go, and the infinite distance of human potential and cosmic wonder. And that, perhaps, is the greatest gift they give us, not the measurement itself, but what it inspires in us, the wonder, the curiosity, the humility, the ambition to reach beyond our grasp, to understand more than we thought possible, to connect with a universe that both contains us and transcends us. We are small. We are brief. We are isolated by light years of empty space. But we are also conscious, curious, and capable of wonder. And in this vast cosmos, that might be the rarest and most precious thing of all. Look up at the stars tonight. See them not as they are, but as they were. And know that you're part of this cosmic story, connected to it all through the light that crosses the years, the space, the infinite distances that separate and unite us all. This is what light years mean. This is how they break our brains. And this is why they're beautiful. And now, as the cosmos continues its silent unfolding, as stars burn, galaxies drift, and space gently expands, there is nothing you must chase. The universe does not hurry. It simply continues. Light travels endlessly, carrying ancient stories across quiet darkness. And you, like a small part of this vast system, may also soften, may also slow. Your thoughts can drift like distant starlight, fading gently into the background. Your breath continues, steady, unforced, natural, just as galaxies move without urgency, just as night exists without effort. You too may rest. There is nothing to solve, nothing to grasp, nothing to reach. You are already part of this cosmic rhythm, not separate, not lost, simply present. So let yourself be carried like light across the years, like a planet in its orbit, like a star in the vast dark sky, not as an ending, not as a beginning, just a gentle pause within the endless universe. Good night, and rest within the quiet of the stars.